mixed language name. It's French and Chinese with a Cantonese transliteration. So the two issues we are dealing with in our work today. The first one is what we call low resource languages. And I had an article with Tanja Schutze in the Signal Processing magazine 2008, and we talked about different challenges of lack of resources in certain languages. I won't go into detail because a lot of you are working on the bilingual project and you know all about challenges. So there are not enough transcribed data, there's not enough pronunciation dictionaries, and very often there's not even enough text data. For example, languages like Cantonese, non-standard languages, standard Chinese languages are spoken but not written, so we don't even have enough text data to train language models. A lot of multilingual speech algorithms are actually language independent because we are all using statistical machine learning approaches. They're language independent, but the systems are often not language independent. And very often in the single research group, anywhere, we lack the language experts. We don't have a speaker of all languages in the single team. So therefore, there's a need for rapid development of multilingual speech systems, and there's a need to meet the challenge of low resource languages for both acoustic modeling and language modeling. Another phenomena my group has been working on for a number of years is code switching. Code switching, many of you might be already, if you are bilingual or multilingual speakers, you will be using code switching all the time. And the actual definition of code switching, well, let's first of all look at some examples. Okay, here we have a English-Spanish example. I seen everything because no corrí nada. And the Chinese example, the most important thing is to induce this EM theory. 很重要的东西是 induce 这个 EM theory. And then the Hindi-English example, student teacher has something, library, book issue, karo. So these are all very common in these languages, and they become sort of its own language, the mixed language, all right? And in fact, these days, even here, I go to Starbucks, you go to Starbucks, and you say, I want to have a cup of grande latte. You're speaking mixed language, okay? And the actual linguistic definition is code switching is the juxtaposition of speech where you have speech that belong to two different grammatical systems, right, or subsystems. So simply having one word, like I just went and bought this laptop computer called Mac. In Chinese, and use the word Mac, it's just a borrowed word. That's not really a code switching language, all right? So, and the challenge, the main language is called the principal language or the matrix language. The secondary language is called the embedded language. So let's just get it. So these are the technical terms, the linguistic terms for code switching language. And code switching itself is a low resource language because there are there's very little collected speech data of code switching, recorded speech of code switching language, and even less, fewer transcribed data because you then need bilingual speakers to be able to transcribe speech in two different languages. And we have recorded some data in lunch conversations where we try to use Mandarin, but we use a lot of English terms. And our transcription team, which is based in Shenzhen, really couldn't transcribe that because they don't know English well enough to transcribe that. And so that's why we have very little. So code switching itself is a low resource language.
So you are not requiring that the embedded language be understandable by the person speaking it?
Of course it has to be understandable by the person. What do you mean?
Are surely the other way around. They're just borrowed. They're borrowed in total. But
No. Borrowed words is there's no. So for example, in here, this whole sentence is in Hindi grammar. And then okay. It's not. I will show more examples later, and I will explain in more detail.
For definition, then, if it's just a borrowed word and you don't understand the other language, does that count as code switching or not?
No, not really.
Someone who orders
yeah, I know what you mean.
Grande latte doesn't mean they speak Italian.
Yeah, they don't. If you say a grande latte, doesn't mean you are code switching. I want to say that's not. But if you are a true bilingual speaker, like a lot of our, because my university is an English language university, but there are a lot of Chinese students, and they are all bilingual speakers. And when we have research meetings, it's code switching. Sometimes we code switch to another language. Belong to two different grammatical systems. This is important.
Yeah.
Okay, so you actually go to another language and follow the grammar of the other language. When you come back, you follow the grammar of this language. And this is very important to our approach. I'll explain later. So yesterday, Morgan and I talked, and we touched upon acoustic modeling a little bit. So that's not today's topic, but I just want to give an overview of what people do for acoustic modeling. For multilingual acoustic modeling, there are very conventional approaches. One is you simply train a separate model for each language. And another approach is you collect a lot of data and you train the same, a universal set of phoneme models with different languages. Or you can do adaptation from one language to the other. And how do you get the sound inventory of all the languages? There are also different approaches. Some people use IPA symbols. Some people use articulatory feature-based units, and others use purely data-driven Fung clustering, so that the data would, the similar sounding speech data will be clustered together. And here's an example of what we did, our early work on Mandarin to English phoneme mapping, sound mapping, and then we use this kind of mapped phoneme units to do Mandarin-English bilingual recognition, including code switching recognition, because when you try to use a single system to recognize both English and Chinese in the same sentence, you must use a single acoustic model. You don't sort of switch between this model and that model. And this single acoustic model is a large set of both languages. And there are different ways of combining these acoustic models. So if you have an English P and have a Chinese P, how do English P train from English sounds and Chinese P train from Chinese sounds? How do you combine them? And again, there are different ways where either people just say those two P are the same P, or they use data-driven methods again. They just lump all speech data together and train a single P model. And or they use hierarchical approach. And our approach, this was also early work, 2001, 2002. Later on, we extended this to multi-accent models. Well, basically what we do is we build a decision tree of a base phone, and then we build decision trees of these variants of this base phone from other data. So for example, you have suppose you have a lot of English data, you build the base phone decision trees from English data, and then you have a little bit of Chinese data, then you build these other variants from Chinese data. And then we do decision tree merging, where we merge the leaf nodes with some kind of acoustic distance measure, and then they share some of the states. Yes?
Yeah, regarding the acoustic, I'm sort of bilingual, but I live in a bilingual environment. My children are bilingual. Bilingual. So we tend to inconsistently use the phonetics of the source language. So I would go to Starbucks and say, can I have a grande coffee?
Well, that is very interesting, because for code switching, we tend to use a pronunciation of the matrix language.
Okay.
All right. If you're speaking English and you mix in Italian words, exactly. Even though you're an Italian speaker, you'll be using English. Exactly.
Yeah.
That's what people do.
Yeah.
All right. So if I say I'm going to Paris next month, I'm not going to say I'm going to Paris next month. Nobody does that. It's just naturally we use the. So that is very interesting. So for acoustic modeling or code switching, we actually need to model the matrix language accented embedded language, right? So anyway, so this is applied to multilingual and also bilingual speech. So that's basically the overview of the acoustic side. Now, today's topic is really on the language modeling side. People have been working on acoustic modeling on multiple languages for a while, for a decade. I think since the late 90s already. But language modeling, multilingual language modeling is a fairly recent topic. And why do we want to do that? Well, one reason is because of the challenge of low resource language. For example, you have a lot of large amount of training text in the resource-rich language, and then you have, you don't have enough resources. You don't have enough text in the a non-standard language, such as Cantonese, right? So you want to borrow. That's what I mean. I want to borrow language model or text from the resource-rich language to do some kind of what we call cross-lingual language modeling to enrich the language model of the resource-poor language. So this is the goal, the challenge. And so what people commonly do is the first thing people do is interpolation. You have speech recognition will always deal with out of domain, new domain data, and then we use interpolation. So if we treat this low resource language as being new domain, we can also use interpolation. Right? In fact, for mixed code speech language modeling, people have been using interpolation for a long time. You use the English language model interpolated with Chinese language model, and hopefully you'll get some kind of a mixed language model. However, I want to point out is that when you use interpolation, there's really not much constraint. You're saying at any word you can switch to the other language for code switching, right? So you don't really have a lot of constraints. So recently people are using interpolation, then they use RNN, but it's still essentially a mixture model. It's not. And another way of doing language model, which is, this is parallel to the acoustic model. People do language model adaptation as well. You adapt one language model to the other with the local language task-specific knowledge. So people used to do that for task-specific language model adaptation, but you can also use language-specific knowledge to adapt the language model. However, these methods, they have their problems. For example, in code switching language model, if you use interpolation, there's really no constraint. You're basically saying you can go from Chinese to English at any word. You can come back at any time, which is found to be, linguistically, it's not true. We don't just switch in any position. So in code switching, what other people have done, which sounds like makes a lot of sense, is that people do language diarization. You detect where you're switching first. So we also did this early approach in the early years where you say, okay, I'm going to try to use a phone recognizer or some kind of recognizer to say, now this word is English or this word is Chinese, and then I switch to language model, right? The problem with that is it's very hard to predict where in the sentence the speaker is switching to the other language. And if you make early decision like that, if you make a switch point decision that is wrong, then your recognition will be wrong. And this is found to be true because this kind of approach gives you very little gain, if any, in code switch speech recognition compared to the baseline interpolation model. Right? It sounds good theoretically, but because code switching point is so hard to detect, so this approach is not very nice, very ideal. So there are other approaches such as using RNN. You just train your code switch model. You collect code switch data, but instead of using n-grams, you train RNN with part of speech tag, and that has shown improvement over the baseline n-gram approach. But I think that really is because when you don't have enough data, deep learning language model always gives you a gain over n-gram model. It has nothing to do with the code switching phenomena. It just models the statistics better when you don't have enough data.
What was the part of speech trained on?
It was trained on the matrix language and the foreign language. Also, I should point out that part of speech tagging of a code switch language is also very, very difficult.
Yeah, that's what I was
yeah.
thinking.
So this approach gives you some gain, but the gain comes mostly from RNN versus n-gram. All right. So, but using part of speech tag, the reason we started also working on that is thought, okay, maybe part of speech tag gives us some syntactic information. They will give us more information about where you switch. But the challenge is that how do you train part of speech tag? And then there are other approaches where people just translate it. They generate, because you don't have enough code switch text. So people propose to generate artificial code switch text. So they translate part of a matrix language text into the other language and put it into training. So here, it's interesting because then you sort of solve the low resource language problem by generating more. But the issue is, how do you generate the code switch data? Because the data you generated using SMT, right? You generate, for example, you translate every phrase to the other language. But are these really code switch points? Do they really occur in real life? You don't know, right? So that's a challenge. So our proposed work is, overall we call it cross-lingual language modeling. But in specific case, we also have the code switch language modeling. So I put these two work together in this because they are actually in the same framework with some differences. And I will point out the difference as we go on. So what is cross-lingual language modeling? So this is a general framework where you have this is your target language, the low resource language, where this is the typical acoustic observation, and then this is the language you want to decode into. So then you usually have this acoustic model here and the language model here. But because this is low resource, so the low resource language model then has to come from a translation model from target language to source language to the target language, and also the language model of the source language, which hopefully is a resource-rich language, right? So this is a sort of a translation model. And then put it together, it's approximately equal to this. So that's how, in general, when we talk about borrowing a language, this is what we do. Now the key here is, what kind of translation model do you do here, right? So in previous approaches, people have tried, one approach is simply lexicon transfer, where PV given W is a transduction model where you just have word-to-word translation probabilities. It's a product of all words, right? So which is assuming one word translates to one other word. All right, this is the simplest. All right, so you can imagine that this is not very good. This is like, this is almost equivalent to the interpolation model where you say any word can go into another word in the other language. So then this is called context independent. And then people would then propose further to do a context dependent transduction. Instead of word to word, it says I look at this translation or transduction model looks at also the context of the previous word, right? So it just tells you that you also look at the previous word. So that gives you more context and therefore a little bit more linguistic syntactic constraints, right? You get more context, you have more data. Now what we propose is something more drastic. It's still the same framework. So we use a WFST framework. So this is just some notations I want people to. So there's C level and H level. This is the search network in the WFST framework, where you compose basically the phoneme model, the state model, the context model, the lexicon, and the grammar, right? And so speech recognition, we use we use C-level search network. So for speech recognition with cross-language models, basically you're talking about this grammar has to be a cross-language grammar, okay? Cross-lingual language model. And in fact, if you do the projection, you also can output two. You can output the language in the source language or the source language or the target language. So in the WFST network, you can take, for example, recognize Cantonese speech into both Cantonese and Mandarin output, right? Now, so and in code switch language, then this part becomes a code switch language model, all right? And what we call code switch language model, and it projects to the. So what we do for code switch language model is we basically, again, borrow, for example, English, and we project into local language, Chinese. And because you have enough of Chinese language modeling data, so if you can project that, if you project code switch language into pure Chinese language, then you can do Chinese recognition, right? But again, the key is the transduction. How do you do the transduction? And we propose that when you do this cross-lingual language model, you must have syntactic constraints. Why? Let me use an example. This is a word alignment between Mandarin text and Cantonese text. A lot of people think that Cantonese is just a dialect of Mandarin, but some of you who have worked on Babel, you know that it is not. It's not a dialect. It's a different language. It's not mutually comprehensible. It's actually more different than Italian and French, for example. Some linguists say that Cantonese Chinese are more different than French and English. So here, if you look at the alignment, then you see why. First of all, even if you don't read Chinese, you see a lot of characters that are very different from one language to the other. And then you see a lot of these alignments. Here, there are a lot of inversions. These are what we call inversion, right? So there's a lot of word order changes, right? So if you want to deal with Cantonese, if you want to borrow Mandarin to recognize Cantonese, your transduction model has to handle the inversions, all right? So here is the same framework where we say that in fact the transduction model itself needs to incorporate a phrase-to-phrase transduction model with a reordering model. The R is a reordering model in there, okay, a reordering sequence. All right, and we train that. So here is another example. So let me just use this diagram to explain our approach. So here, this is a Cantonese sentence, and this is a Mandarin sentence. This is the training data of Cantonese to Mandarin bilingual sentences, right? From this training data, what we can get is, these are word positions, and then we use a word alignment. Okay, we have these word alignments. And so we do several things. One is grouping words into phrases. For example, here, if two words align to one word here, then this is considered one phrase in Cantonese, right? So, and then here we have this phrase alignment, okay? So we have this end-to-one phrase-to-phrase alignment. We also have this inversion alignment, okay? And then we need to basically parameterize the reordering. All right, we also learned this phrase transduction from parallel data. Now, you ask where do we get the parallel data? So we have some Cantonese data, right, transcribed data. It's not enough to train a very good statistical n-gram model. It's not large enough, but it is enough to give us this kind of information, right? All we try to learn from here is the reordering transduction. The reordering in the transduction model. Okay.
So you have a parallel corpus of Cantonese Mandarin.
Well, we have Mandarin, yeah. So, for example, for any Cantonese data you have, if it's not a whole lot, you can easily translate into Mandarin, and then you can train your parallel data. It's just not hard to do.
Manually or automatically?
Translation, it's up to you. Probably automatically and then post-process manually. What we have, I will explain, what we have is that because Cantonese is not a written language. So in Hong Kong, for the Hong Kong Legislative Council speech and debates, all the transcriptions are in standard Chinese, which is Mandarin. So all the official documents, official transcripts of Cantonese speech are actually in Mandarin. So we don't have to translate it. We already have that in our data. We just have to transcribe maybe 11 hours of Cantonese speeches. All right. So our task really is we have a lot of transcribed data of Cantonese, but it is not in Cantonese, it's not verbatim transcription. It's actually translated also into Mandarin. So we use that. And that data is available on the website. You can download it anytime. You can use a lot of this. So, and the next thing we do, so here is the WFST segmentation model, where you then have, you combine words into a phrase, for example, right? And then there's a reordering model. We experimented on 3 kinds of reordering model, namely local constraints, three kinds of constraints, namely local constraints, IBM constraints, and ITG constraints. I will explain in the next few slides what they are. And we parameterize this reordering probability of R1 and probability of RK given RK minus 1 by assigning decreasing likelihood to phrase reorderings that diverge from the original word order. So the more you're different from the direct word order, if you invert or if you do something else, then we assign a decreasing likelihood up to a certain point. Now, the constraints. These are constraints people use in statistical machine translation, local constraint, IPM constraint, ITG constraint. Local constraint simply says that one phrase can jump and most L-1 phrase positions, either forward or backward in the other language. Right? That's a local constraint. And the IBM constraint says that any phrase in position RK can be selected from the positions of the first M yet uncovered phrases. Right? And then there's the ITG constraint, inversion transduction grammar constraints, where it says your permutations, it is forbidden to have permutations, these two types of inside out, outside in kind of permutations. And this never occurred in translated texts in any language pair. Right? So this is basically says you can reorder words except for this kind of reordering. Okay, this can never happen. Turns out that will cut down a lot of permutations that you don't need. All right. So in statistical machine translation, people have experimented on these three constraints and found that ITG constraints give you the best performance. We also did experiments with these three constraints. We also found that ITG constraints give us the best performance in both in terms of Cantonese recognition and in Cantonese to Mandarin translation. And then, so this is again the phrase-to-phrase transduction model where now we incorporate the reordering model in there. And we learn the phrase, the phrase table from parallel corpus. Right? Now, in certain language pairs, you don't really need to have the same corpus to train your language model and the translation model. So we have a lot of, so if you're doing, say, English-Chinese, then you have a lot of English-Chinese parallel data for other tasks you can use, right? Because we are just learning the word order constraints. Right? And then at the end of the WFST framework, you then reconstruct the whole thing back into your target language. So in this case, it will be Cantonese. So what we did is basically, essentially this. Okay, let me show you. Yeah, here. So what we did is that we say, okay, we have a Mandarin language model. We have we segment Mandarin speech into phrases. We reorder it. We reorder Mandarin words, and then we also translate Mandarin words into Cantonese, right? And then we reconstruct, and this whole thing then becomes my Mandarin to Cantonese translation model, right? I compose with a Mandarin language model that gives me my Cantonese language model. So this is what we.
Language model is a character level language model, right?
It doesn't matter. It could be character because at the end we just want phrases, so it doesn't matter.
I see, but your segmentation transducer, the S there.
That's into phrases.
Could be either.
It could be word.
Or word-based.
Yeah, because word and phrase in Chinese is basically the same thing. You know, what is the definition of a word in Chinese and a phrase? It's basically the same thing. So of course, if you use character-based there, you have character-based back here. Anyway.
It seems to me these transducers could get very, very large. So do you have a sense for how big the various transducers are here in terms of like memory and time to actually do this?
We use the WFST3 decoder, so it's just 1 times real time. It's not that.
Okay, so it's actually not that big.
Yeah, it's not that big.
Do you use your implementation of the WFST?
So we use OpenFST, and then we use the T3 decoder we got from Tokyo Institute of Technology, and we have changed that to a online streaming-based version, but it's basically OpenFST. I'm sorry?
Is that available?
Yeah, we will ask them if they let us, they give it to us for research.
You have to use the lazy implementation. The lazy implementation, want to increase the network just in time or static?
So for these experiments with static, yeah, for these experiments.
I'm sorry, this R transducer, I'm still not entirely, is that just projecting it onto the Cantonese?
This R here, this is a reordering projection.
The R, the first.
Oh, the R, this is reconstruction. It's just reconstructing into Cantonese. Yes, projecting into Cantonese.
Okay.
Reconstructing back to Cantonese. Because imagine I don't have enough. So if you intuitively speaking, it's like this. Okay, I don't have enough Cantonese data. So I'm going to say, I take Mandarin speech, text, Mandarin sentences and say, which of these words will be in the, would need to be translated into Cantonese? And which of them need to be reordered, right? So I segment them, I translate some Mandarin words into Cantonese words, and I reorder them. Then it becomes my Cantonese language model. So,
I have
yeah.
one question. Even though the amount of Cantonese data is small, why don't you also use P of V?
P
like
of
G in Cantonese. You are only using.
No, we do use Cantonese.
G in Cantonese according to your previous formula. So if you go back a few slides back, you said you are using. Go back.
This is translation.
Yeah, here you said you are using pi of G.
Here, you mean?
Right.
Yeah.
Why don't you also mix it with just G, like an interpolation of pi of G with G?
Why don't we do that? We use all the Cantonese data in our parallel data translation.
But you are only using the translation model.
We are using translation model in the.
Good old LM trained with small amount of Cantonese data. Interpolated with this project.
We use that as a baseline model to compare. Yeah, but yeah, sure. So yeah, sure. So we go forward. I'll talk about those experiments later. Now, so before I talk about experimental setup and results, I'll move to code switch language modeling. You will see that it's in the same framework with differences, okay? Again, it's a code switch language model with syntactic constraint. Now, we'll look at an example of a code switch sentence. So this is a Chinese sentence, pure Chinese sentence, 很重要的东西是包括这个 EM 理论, which means something very important is to include the EM theory. All right? And if we align these words or phrases again, and we get this kind of alignment, including inversion, right? Right. Then we can generate a lot of hypotheses. We can say, switch from here to here, then go on, or switch. You go Chinese, and then you switch to English, and then go on. You can just switch back and forth. In the interpolated model, that's what it means. Any word can. So you have a whole bunch of these hypotheses. But however, we're saying that some of these hypotheses is permissible, others are not. Which are not permissible, it's very important. For example, something here, these two are not permissible. Whereas you say very 重要的, very 重要, let me try to do this. 很, so you have Chinese first, you say 很, and then you go, I'm going to switch to English now. 很 important something. So you translate this to English, translate this into English, you say 很 important something is da 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 da. Right? But that's actually not permissible. And I will explain why. Linguistically, it's not permissible. You just don't switch like that. And turns out linguists, where's that constraint? Turns out there's a linguistic code switching constraint, which is called equivalence constraint, which says that if you must follow, whenever you're in one language, you follow the grammatical structure of that language. So whenever there's inversion, then you're violating the grammatical structure of your matrix language. So if you say 很 important something, then you actually violating the grammatical structure of this when you go into English. Do you know what I'm saying? So if you go into English, you must follow English grammar. When you come back to Chinese, you follow Chinese grammar. So whenever there's inversion, there's a violation of that. So then when we're saying that, okay, I can say that, syntactically speaking, whenever there's inversion, you cannot switch. So that gives me the syntactic constraint on code switch language model. If you know where there could be a possible inversion, then you say there you cannot switch. Okay? So for code switch language model, 2 constraints. 1, this code switching must occur at the phrase boundary, not character boundary, but phrase, in Chinese phrase is a word. So it must occur at the phrasal or the word boundary, which has the equivalent in the other language. Number 2, it must occur where there is no inversion in the other language. Right? And the rest is just implementation, WFST network of the same thing. Now, if we look at this same example as previously, well, all we have to do is that instead of word alignment and phrase alignment, we add an additional layer, what we call chunk. These chunks are common to both English and Chinese. So whenever there's inversion, though, what we say is that you either translate the whole chunk in the other language, or you don't translate at all. So whenever there's inversion, you either go into something very important, the entire English phrase, or 很重要的东西, the entire Chinese phrase. You cannot switch in between. Right? So this is the same diagram as before, except we have additional chunk layer, right, with this constraint. That's all. Right? That's all. So similar to before, in the transduction model here, we have a reordering model and a chunking model. We have additional chunk segmentation model and a reordering model. Okay, so this is similar as the previous phrase segmentation model. Instead of phrase segmentation, we have additional chunk segmentation. And then the translation will be chunk-to-chunk translation. Something very important must be translated entirely into the Chinese equivalent and vice versa, and not just word by word. Okay? So the transduction, then this is a reconstruction model similar to the previous approach, the same framework basically. So the only difference here, all right, we have, let's see. So our target, okay, that's good. Our target is the code switch language model. Our source will be, our target is Chinese and source is the other way around. We're borrowing English into our code switch language model. Okay. So what are we generating? Here we have this chunk translation model, reconstruction model, the reordering, the segmentation of chunk, segmentation of word. And the code switch model is this tile composed with the language model. In this case, it's actually the Mandarin language model. So what we are saying that when we are trying to recognize Mandarin switching into English, we're trying to recognize Mandarin speech as our base language model, but with some kind of English translation in between, subject to some reordering constraints. All right? So how do we train? Okay, so then now we have 10 minutes, we look at the experiments then. So for low resource language model experiments, we compare, so this is just experimental setup. As I mentioned, we use Hong Kong Legislative Council speech with transcribed Mandarin sentences. We also transcribe 19 hours into Cantonese. And we use part of it as training set, development set, and test set. And then we have part of it, we use the verbatim manual transcription, the written Hansard transcription as parallel data to train the alignment model. Oh, I'm sorry, we did use interpolated model. I just thought, yes, we did. It's an interpolated model. all right? It is an interpolated model with a set of Mandarin transcription with parallel text data to train a word-level interpolated trigram model. And then we compose with the TAL to give us the cross-lingual language model. All right. This is just a reminder. Oh, evaluation, how do we do that? So what we do is we recognize Cantonese speech both into verbatim transcription and into Mandarin output, because verbatim transcription in Cantonese is not readable. Nobody can understand that. So we actually also output the Mandarin translation. So it's kind of like a speech translation there. And therefore, we evaluate by 2 scores. One is the word error rate score, evaluation on the Cantonese output, and the blue score evaluation is on the Mandarin output. Okay. And this is evaluation of phrase transduction versus word level transduction. And obviously, phrase level gives us better performance. Okay. Here is the effect of reordering model. Again, ITG constraints give us better performance in terms of improvement on blue score and reduction in word error rate for ITG constraints. So in conclusion, for cross-lingual low-resource speech recognition, we propose a reordering model to address the syntactic discrepancies between resource-poor and resource-rich languages. All right, in theory, you can imagine you can borrow resource-rich language in any other. You can borrow English for Cantonese if you want. It's just the parallel data has to be of good quality. And we have obtained performance improvements. This same system can be used to improve spoken Mandarin speech recognition to output written Mandarin. So for example, we have a project where we have to transcribe, to do closed captioning of a meeting speech. And when people are talking colloquially in Mandarin, and you want to have a nicely written transcription, then you can use the same method. So it would be colloquial speech to standard written language translation. For the same thing, it helps with spontaneous speech recognition and speech translation. We actually solve the actual speech translation, end-to-end speech translation framework that can be used for speech translation. So imagine you have a lot of parallel data and the input is English, you can output Mandarin using the same framework. But it would be an end-to-end WFST-based speech translation framework. In code-switching language model experiments, again, we only have 20 hours of code-switching lecture-speech corpus and 163 minutes of lunch conversation. I think we got tired of recording lunch conversations. because I tell you why, because we normally have our meetings in English. So for this purposes, we actually had lunch meetings where we spoke in Mandarin and occasionally switching to English. It was just too hard for me.
What do you talk about?
Oh, we talk about news, elections and whatever is going on, because we can't really we had a hard time holding down like a Mandarin-based conversation with my students. So usually,
Visiting American NSA contractors.
Yeah. Anyway, so we'll continue with this effort as we continue with the work, but I think some students got tired of doing the recording, but we'll continue with that. We also got this lecture speech corpus from Taiwan, from Professor Li Linshan's lectures. So that's why you get all this, HMM, EM theory, all that. Anyway, text corpora. We have speech processing conference papers, PowerPoint size web data to train for this topic. And we use Gale conversational speech transcription to help with this conversation corpus. It's not ideal. All right. So we have, for the alignment. So how do we get alignment data? We want to have more parallel data, right? And when we try to get parallel data of English and Mandarin from the translation group, there's a whole bunch of news article translation parallel data. So for conversation, we basically will say, okay, how do we generate more? So basically, we use machine translation to translate a whole bunch of collected conversational data. And because machine translation gives us alignment already, so that's kind of convenient. All right. So we compare it to the baseline interpolated language model and to a monolingual language model, adapt them to code switch, and then the code switch model. All right. I just want to show you the final slide. So we've got the best ever improvement on code switch speech recognition. If you look at this, we got almost more than 5% relative improvement over the non-adapted language model. This is interpolated language model already had the improvement, and we have 5% improvement, relative improvement on the. So this is higher than any other approach we have seen so far, and I believe it's really because of the syntactic constraints.
What percentage of these corpora are in English?
The two of them. I remember for lunch conversation, it's about 20%. It's a lot. Yeah, because it's actually me.
Experiments.
Sorry?
If you do a cheating experiment, if somebody tells you that this part is in English, does it give you a lower bound performance?
You mean if you constrain, you say that I know the code switching point already? We did that. I don't remember. We don't have the results here. That sort of gives you the, yes, we did compare to that. It's not, yeah, because that gives us an idea about how bad the acoustic model and the error thing is. Yes, we did compare to that. It was also not very high. So we had the largest gain for code switch language modeling that's being reported. There's another code switch database from Singapore, but I want to point out that Singaporean Mandarin and Singaporean English are very different from Chinese Mandarin and American or British English. So we use our Mandarin, it's sort of a totally different language. It's difficult for me to understand, actually. Singaporean, not just Singaporean English, Singaporean Mandarin is difficult for us to understand, both acoustically and grammatically. Vocabulary is different also. So again, it's the first ever empirical implementation of the syntactic constraint, equivalence constraint in code switch linguistic theory in the language model. And a first ever statistical language model of code switching speech that incorporates syntactic inversion constraints. What else? Code switch speech recognition with the highest relative improvement. We'll continue working on this with different ways of incorporating the equivalence constraint and see if we can get more there. All right, thank you very much.
You. Questions? I have a question. So I guess you developed a recipe for doing that, although do you plan to try with different pairs of languages and stuff?
Oh yes, very good question. We're also experimenting with Hindi English. We collected some Hindi English speech data, and one master student's working on that for his master thesis. The same framework, but for Hindi English.
Yeah. Do you find enough studies to understand what an impossible?
You mean linguistic theories?
Yeah.
So basically, linguists pretty much agree that when you have this kind of inversion, you don't
That's
switch.
for
Any language. In my own personal experience, I switch. I'm a code switch speaker in any language pairs, and it is true. Yes.
So very interesting. Thank you. One area that we work on is Arabic, the change between the dialect and modern standard Arabic, and even within the dialects.
Yes.
And in a different context, not speech and text. So I'm wondering, over there, the code switching is reflected at a layer of morphology, for example. So you kind of need to embed some part of morphology, like as a different layer of information, rather than just the surface word form. So if you want to, have you thought of any way to go beyond that, like have a second layer which is like morphology information?
Very interesting, because if you look at this code switching layer, the diagram. Oh, here. Here. If you look at the code switching dial, because in Chinese, a lot of times when we call morphological changes, actually syntactic change. And then like for Hindi English, I'm not a Hindi speaker, but I know some Hindi. The verb karo means do something. So you often say something something karo, okay? Kind of equivalent to Japanese suru. So you want to say, if you use an English word and then you add that Hindi word to mean it's a verb, you know? And is that morphology change or is that syntactic change? It's hard to define in such a case. So I would say, I don't know Arabic, so I would venture to hypothesize that you can still have a layer, I mean, maybe in between, where you do that. I don't know whether there's inversion or anything like that. So in Hindi English, then you cannot have inversion. You cannot put a karo before the verb, English verb. Yes?
Sorry, I'm intrigued by the relationship between Cantonese and Mandarin. When you want to write down the Cantonese verbatim, what do you do?
What does it look like? Oh, what do we do?
What vocabulary do you use?
It's arbitrary. Okay, there's some example. I have, okay, here. So here's some example of Cantonese transcription, right? And these are like these words. This word, this word, this word, these characters. They're not Mandarin characters. And you look at them. If you don't speak Cantonese, you don't know what it means. For example, this character "koi" means he or she. So the Mandarin "ta" is this Cantonese word. So some of this is conventionally accepted. If you want to write "koi," that's the way you do it, which is basically the character "go" with a person on the left-hand side. It was invented. And then there are other characters that are invented that are conventionally accepted. But very often, even 10 years ago, there were Cantonese characters where people just write the phonetics. Because we don't know what to write.
Is there a conventional system for writing Cantonese verbatim?
Now there is, because now in Hong Kong, since the handover, there are some newspapers that are written in Cantonese. And nobody, if you don't know Cantonese, you don't understand.
A similar situation for Swiss German? That's not applied?
Well, that's always phonetic. Cantonese,
actually, I think in that case, there's pretty long.
There's straightforward way.
There's always been, a small community of people who want to express themselves. But so is it a phonetic? It's not a phonetic spelling. I mean, it's not a phonetic writing system. It's just.
It's not, but it is. It's composed.
That were just created for the purpose of.
I don't know if they were created or they already exist in the vocabulary and people use it, because there are a lot of Chinese characters we don't use. So, and before, it's only in the last 10 years you start to see verbatim Cantonese transcription in advertisement on buses and stuff. And before then, Hong Kong never use that kind of language as a written language. So, but in the last 10 years, you see more and more of that in newspapers and magazines. And but it's kind of strange because it doesn't have a long history, it's not a literary language, so it's just verbatim transcription.
The Hong Kong Hansards are really
written language.
It's a
Mandarin
rendition of what someone said in Cantonese.
Yes. Yes. All official documents are like that. It's Mandarin, but it's almost half classical Chinese, half Mandarin, kind of. But the grammar is Mandarin. But a lot of words Hong Kong use are classical Chinese, old Chinese words because of the history. But at least Mandarin speakers can understand such written documents. They cannot understand verbatim Cantonese transcription.
Would a Cantonese, like a Hong Kong person, would they know what the equivalent Cantonese was when they read the transcript, the Mandarin transcript?
Hong Kong person can always read a Mandarin text, and they understand.
I understand, but would you be able to reconstruct what the original Cantonese was?
Nobody can reconstruct. They can sort of generate how to say the same thing in Cantonese, but there are different ways of saying the same thing. Yeah. Yeah. But when you read, so in school, okay, in Chinese classes in Hong Kong, used to be you would read everything in Cantonese. The pronunciation is Cantonese, but the text is Mandarin. All right, so if you have to pronounce it, you pronounce in Cantonese of a written Chinese text. But when you do that, you do not sound like you're speaking Cantonese. You just sound like you're reading from a text. And it's like I know one French person, a friend of mine, who always pronounce all English words as if it's in French. You can do that, you know. You can, of course, do that. You can use a French TTS on the English text. Okay. That's what she does.
Italians do the same.
Italians. So I can never understand her English because the pronunciation is totally French. She just doesn't even make an effort. So, yep.
All right, thank you.
Thank you.
The conference call now.
Mm-hmm.
Then